electricity and magnetism, a good set of variables and magnitudes have vector nature. That is why we need to have the ability to work with vector function and operators that appear in the physics involved. A scalar is defined as a real number, such as the temperature or the pressure. A vector, on the contrary, is defined by its magnitude, its length, and its direction. It can be represented by an arrow of a length given by the distance between one point and another point. In an intuitive way, we can think of a vector as a variable which is given by its magnitude and its direction. Among vectors, we can define several operations such as addition. The sum of two vectors, a and b, is another vector z equal to a plus b, whose components are found by summing the components of vectors a and b. The product by a scalar alpha is another vector whose components are obtained by multiplying each component by a real number alpha. The scalar product or dot product between two vectors is a scalar defined by a dot b. From the dot product, we can define the magnitude of a vector a as the square root of the dot product of the vector with itself. From trigonometry, we can give a geometry meaning for the dot product. We know from the law of cosine that where theta is the angle between a and b. Vector product or cross product. The cross product of two vectors is another vector a cross b, whose components can be calculated with the determinant of the matrix. The magnitude of the cross product is corresponds to the area of the parallelogram of sides A and B. Remember that the direction of A cross B is perpendicular to A and to B. We talk about a scalar field when each point in space is associated with a scalar. We talk about a scalar field when each point in space is associated with a scalar. That could be temperature, or pressure, or the height in a mountain. Mathematically, we define a scalar field with a function that depends on all three space coordinates x, y, and z, and it can also depend on time. We talk about vector field when each point in space has a vector associated to. Examples of vector fields are wind velocity or acceleration of molecules of a gas. The way we represent a vector field is with a vector function that gives the vector as a function of the position. But there are somewhat more intuitive ways of representing a vector field. Draw vectors as arrows with magnitude and direction in some of the points in space, or draw tangent lines to a vector field in each point. These are referred to as field lines. By convention, the number of lines crossing a surface area is proportional to the magnitude of the field. We define gradient of a scalar field as a vector such that its dot product with the length differential dl, which is the x, the y, the z, gives the change of the function between 2 points, where dl is the infinitesimal vector that gives the direction in which the change in the scalar field is. The gradient of a scalar field is a vector field. It measures the rate of change in space of that scalar field. We compute it as we can define the NABLA operator as If we consider a family of surfaces where a scalar field has the same value, the NABLA operator between any 2 points in that surface, in any of those surfaces, is going to be 0. The gradient of the function is 0. There, the gradient is a vector perpendicular to the surfaces. Think of it as a path in a mountain. If all the points in the path has the same height, there's no gradient in the direction of the path, and the gradient will be perpendicular to that path. The concept of flux of a vector field is very interesting and important in electricity and magnetism. If we think about a fluid with all the particles moving in a particular direction, it is more intuitive to think about the flux of those particles across a specific surface area. But we can define the flux of any vector field. We can just think about how many field lines are crossing that particular surface area. This mathematically can be written as this, where A is the vector field, S is the surface, ds is the differential of surface, and n is the unit vector perpendicular to that surface. The divergence of a vector field is a scalar defined in every point of a space, that is, a scalar field. Consider a closed surface S which encloses a volume delta V. Inside that volume there is a point P where we want to calculate the divergence. The divergence is given by the flux. This divergence is given by the flux of the vector field through the closed surface divided by the volume in the limit where the volume goes to 0. We can calculate the divergence of the vector field with the NABLA operator.